Hello all. In this video, we are going to learn about Markov decision process. So what is a Markov decision process? It is a mathematical framework which is used to describe an environment in decision making scenarios where outcomes are partially random and partially under control of a decision maker. Markov decision process provide a formalism for modeling decision making in situations where outcomes are uncertain, making them essential for reinforcement learning. MDP is used to formalize the reinforcement learning problems. If the environment is completely observable, then its dynamicity can be modeled as a Markov process. In MDP, the agent interacts with the environment and performs actions. At each action, the environment responds and generates a new state. The Markov decision process can be represented in the mathematical form as a tuple form, and it consists of 5 tuples S, A, P, R, gamma. So what is S? S is a state space. It means that it represents a finite or infinite number of states, and these states represent the environment. The next one is A, which is an action space. This is a set of actions available for the agent at any state. The next one is P, which represents the transition probability. It is a probability function P of S dash given S comma A, which defines the likelihood of transitioning from a particular state S to the next state S dash after performing an action A. The next one is a reward function R. This is represented by a function R of S comma A comma S dash. This assigns a reward for moving from the current state S to the next state S dash by doing an action A. The last tuple we have is gamma, which is said to be a discount factor. This discount factor is a value which ranges between 0 to 1. This determines the importance of the future rewards. The next concept in MDP is policy. What is a policy? The policy defines the agent's strategy for selecting actions in each state. This policy can be either deterministic or stochastic. The deterministic policy is represented as pi of s. It means that always it selects a fixed action from a given state or for a given state. The stochastic policy is represented as pi of A given S. It means that it assigns probabilities to different actions for a given state. Now we will see an example for MDP. Here we have an environment with 3 rows and 4 columns. This is the first row, second row and third row. Similarly, we have 4 columns, first column, second column, third column and fourth column. The agent can start from the cell 1, 1, and here in the cell 3, 4 there is a treasure, and when you consider in the cell 2, 4 there is a fire. So there are 2 goals here. The agent can move to a treasure goal or it can move to a fire goal. If the agent moves to a treasure goal, then it is a positive goal, and if the agent moves to a fire goal, then it is a negative goal. And in between the agent, there is a place which is said to be a pit where the agent should not move in. So this can be represented in a matrix form as this way. So the agent can start from the cell 1, 1 and it can move towards the goal which is there in 3, 4 or in 2, 4. So if the agent moves to 3, 4, then it is a positive goal, and if the agent moves to 2, 4, then it is a negative goal, and in between we have a pit. Now we'll see all the 5 tuples related to this environment. State. So state is a position on the grid like a cell 1, 1. So here there are different states. 1, 1 is a state, 1, 2 is a state, 1, 3 is a state, 1, 4 is a state. Similarly, each and every cell represents a state in this environment. Then action. There are 4 different actions for this environment: up, down, left, right. The agent can move either upwards, or the agent can move downwards, or leftwards, or rightwards. So consider the agent is in the position 1. Now the agent tries to move to the cell 2, 1. So the agent will be doing a action up, and from here again, for example, from here the agent tries to move to the cell 1, 3. Then the action the agent needs to make is an up, and from here the agent is doing an action down. Then the agent will be moving to the position 1, 2. And for example, the agent is in this position, and now the agent is moving a right direction. So it will be moving to the position 1, 3. The next one is the transition model. This is represented as the probability value. The transition model tells us what happens when an action is taken in a particular state. It's like asking, if I move to right from here, where I will be landing up. Sometimes the outcome is not always the same. That is an uncertainty. For example, the transition model provides 80% chance of moving in the intended direction, 10% chance of slipping the intended direction. So we have the probability value. This randomness is called a stochastic transition. Next one we have is the reward. A reward is represented as a number, and this is given to the agent after it takes an action. If the reward is positive, then it means that it is a good move. If the reward is negative, then it means that it is a bad move, or it means that a penalty for whatever the action it has done. So for example, in this case, +1 is the reward given to the agent when it reaches to the goal state, and -1 is the reward given to the agent when it reaches to the negative goal. And for example, if it moves between any non-goal states, for example, if the agent is moving from one cell to another cell, which is non-goal state, then it gets a reward like, for example, it can get a reward like -0.1. The next one is policy. Policy is nothing but it is the agent's plan. So now here we will see an example for policy. A policy is an agent's plan. It tells the agent, if you are in this state, take this particular action. The goal is to find the best policy which helps the agent that can earn the highest total reward over the time. So for example, this is a sample policy. Here a sample policy is given for this example or for this environment. This is the sample policy, and here the reward value is given as R is equal to -0.04. This is for when the agent moves between a non-goal cell. For example, this is a example policy. Okay, so the agent can move from the first cell to the next one, and then from here to here, and then from here to here, and so on, and it can reach the goal. And when you consider this particular cell 1, 3, it's actually having two policies. Either it can go this way or it can go this way to reach the positive goal. Markov property. So what is a Markov property? Actually, MDP follows a Markov property. This states that the next state in the current environment depends only on the current state and the action. It does not depend on the past states. So mathematically, this is represented as, that's the likely probability. This is the likely probability. P of S dash given S comma A. S is the current state and A is the current action performed. This ST minus 1, AT minus 1 are the previous action. So whatever the previous actions have been done, the Markov property says that MDP follows only the current state and its action. The current state and its action gives you the next state. So for example, the agent is here. Okay. And now if the agent is making an up move, then the agent will be moving upwards in this direction. So the previous action, it won't consider the previous action of the agent. The previous action may be this way, it might have moved this way and now it may be coming this way. So whatever the previous action may be, it won't consider all those previous actions. All the previous actions will be nullified. It considers only the current action. So what is the current action? The current action is the current state is here and it does an action up. So it moves to the next state and this is said to be S dash. So this likelihood probability is based on only the current state and its current action. Now we'll learn about the value functions and the optimal policies which we use with MDPs. So this is actually based on Bellman equation. So we'll learn what is a Bellman equation. The Bellman equation is used to determine the value of a particular state. It states the value of a state which is equal to the immediate reward plus the expected value of the next state. This allows an agent to make better decisions by taking into account both the current and the future rewards. So these future rewards are important. When we consider this Bellman equation follows the principle of optimality. This principle of optimality means the optimal value of a state depends on its immediate reward and the value of the next state. Now we'll see what is state value function. The state value function is denoted as V of S. V is value and S is state under a given policy pi. So V pi of S is equal to E. E is nothing but expectation. It means that the average value, okay, of R S comma A. R is nothing but the reward. Then gamma. Gamma is the discount factor. Then V pi of S dash. That is with the previous iteration. Okay. Then we can expand this equation with transition probabilities. In this equation, we are not using any transition probability. So we can expand this particular equation using the transition probability. So our equation will become V pi of S is equal to summation of A belongs to the action set capital A pi A of S. Pi is nothing but the probability of taking action A in state S under the given policy pi into summation of S dash belongs to S. So S dash is the possible next states. So what we will be summating? It is the transition probability P of S dash given S comma A. S dash is the next state and S and A are the current states into the reward value for the particular action as well as in the particular state plus gamma the discount factor V pi of S dash. Next we will learn about the action value function. The action value function is defined as the Q function. Q function is represented as Q of S comma A and this represents the expected return for taking an action A in the current state S and following the policy pi. So we get the equation as Q pi of S comma A. S is the current state and A is the action performed is equal to E. E is nothing but, as I told you earlier, it is the expectation as well as expectation average. What will do the average? Average of R, that is the reward for whatever we are getting from the current state. When we do the action, we will be moving to a next state. So whatever reward we are getting, that reward plus gamma into V pi of S dash. Then we can expand this equation with transition probabilities. When we expand this equation with transition probabilities, we will be getting Q pi of S comma A is equal to summation of S dash belongs to capital S, the transition probability into the reward Rs comma A plus gamma into summation of A, the actions. Here we use the probability, that is the policy probability, that is pi of A dash given S dash into Q pi of S dash comma A dash. So this is said to be the action value function, that is the Q function. Now these two functions, that is the state value function equation actual as well as the action value function equation can be optimized. So when we optimize it, we'll get the optimal policy pi star. Okay. So we'll see what is the optimal policy pi star for the Bellman equation. So the first one is the optimal state value function. So it is defined as V star S is equal to max A of summation of S dash, the transition function into the reward plus gamma V star of S dash. Similarly, we can find the optimal action value function, that is the optimal Q learning. The optimal Q learning is mathematically represented as Q star of S comma A is equal to summation of S dash, the transition function, the reward plus gamma max A of Q star S dash comma A dash. Now we will see an example for optimal state value function. So what is the optimal state value function? This is the formula for the optimal state value function which we have seen in the previous slide. So what is the key idea? The key idea is to solve iteratively via the dynamic programming. So from where we will be starting? We will be starting the value for any particular state as 0, and then we will be applying this equation, optimal state value function equation, and then we will be trying to find what is the value for each cell. So how to iterate? We rewrite this particular equation into as we are iterating, we rewrite this into I and I plus 1. I is the current iteration and I plus 1 will be the next iteration. Okay, so in that manner, so we are rewriting this equation. We'll see the same example. So the equation, whatever we have rewritten is given here. And now the reward, already we have seen this is the reward, plus 1 for positive goal and minus 1 for negative goal. So the discount factor here it is gamma is equal to 0.9 and the reward, initially the reward for any cell will be 0 and the noise is 0.8. So it means that if it does the proper move, then the reward will be 0.8, and if it does the negative or wrong move, then the reward will be 0.2. Okay. So in the first iteration, what we do is we will be giving the value as 0 for any cell. Okay. So that is the first iteration. In the second iteration, as we know, in this environment, we have given that the goal state as positive goal state and negative goal state as plus 1 and minus 1. So we are marking it as plus 1 and minus 1 in the next iteration V1. So this is V1. In V1, we have plus 1 and minus 1. The remaining values are all zeros. Now we are going to find what is the value for this particular position. So how to find the value for this particular position? We will be using this equation. So how to apply this equation? So consider we are in this position. To find the value, consider we are in this position. And now there are 3 moves here. We can move rightwards, we can move leftwards, as well we can move downwards. If we move rightwards, then it is a positive move. Okay, if we move leftwards, it is not a positive move. Similarly, if you move downwards also, it's not a positive. Now, what we do is, we rewrite this equation. V of I plus 1, yes. So what cell value we are going to find? We are going to find for 3,3. So it is version 2 or iteration 2. For iteration 2 we are going to find. So it is V2, value 2, iteration 2 of 3,3 is the state. The state number is 3,3, which is equal to summation of all the different states on performing the action. So it moves to 3 different states, rightwards, leftwards as well as downwards. So there will be 3 different moves we will have. So for all the 3 different moves we need to do, and then we need to take a addition of it. So what is this probability of S dash given S comma A? So S dash is the next state. What is the probability of moving to the next state given the current state is 3,3 and the move which we are going to do is, for example, right move. If we do a right move, then we will be reaching the goal. Into the reward. What is the reward? Okay, reward, that is S is the current state. In current state, and when we do a, for example, when we do a right move and then the next state, whatever state it is, if that is the case, then what will be the reward? Plus 0.9. What does this 0.9 represent? 0.9 is gamma, the discount factor 0.9 into VA of S dash. VA of S dash in the sense, in the previous iteration, what it has happened. Okay. So now we are going to rewrite this equation. So first we have the probability of S dash given 3,3 right. For example, if it is right, so from 3,3 it is moving towards the right direction. So it is a good move. If it is a good move, here we have mentioned it as noise as 0.2. So if it is a good move, then 1 minus 0.2. So it is 0.8. So here we will get 0.8 into the reward value. So what is the reward value in this iteration? V1 iteration reward value, it is 0. Here it is, the reward value is 0. Okay. Plus 0.9, this 0.9 here into Vi of S dash. To which state we will be moving? We will be moving to this state. Okay, we are trying to, from this state, we are trying to move here in the next iteration. So what is the value here? It is plus 1. So it is 1. Okay. Next we do a left move. So from here, from the agent is in this position 3,3 and then it moves does a left move. So left move, what is the noise point to? Here there are two noise. One is to the downward as well as to the left side. So the noise is divided by 2. So you'll get 0.1 into what is the reward value? Reward value will be 0. Okay, 0 plus 0.9 into VA of S dash. In this iteration, in ith iteration or the first iteration, what is the reward value? The reward value is 0 here. So it is 0. So you'll get this value. And then the next move is a downward move. Okay, the next move is a downward move. So in this downward move, the noise is, as I already told you, the noise is divided by 2. So it is 0.1 into 0. How we get the 0? That is, what is the probability of moving? From 3,3 to downwards. Okay, so it is 0 plus 0.9 into 0. 0 is the value which we have in the previous iteration. So it is 0. Now we add all these three. This one, that is the right move, the left move and the down move. When we add all these three, we'll get 0.72. So our value for this particular cell is 0.72. Okay. Now we get in iteration 2, we get the value for 0.72. Similarly, in next iteration, when we calculate for, you can calculate for this cell as well as this cell, because the neighbor for this particular cell 3 comma 3 is 3 comma 2 as well as 2 comma 3. So we will be getting values for these two things by applying the same formula. Okay, so we get the value. Similarly, when it will converge, actually you have to do multiple iterations until you get the value for each cell by applying the state value function or the optimal state value function. This is all about Bellman equation and MDP. Thank you.